We're going to look at another exponential growth model that models population, and we'll talk about why perhaps exponential growth is not always the best option for modeling population. So we've got a population of birds growing at a rate proportional to its current population. In other words, dp dt is equal to k times p. And we've already seen that we can solve that differential equation and find that p is equal to c e to the kt, where c is the constant of integration and k is the constant of proportionality. And we can solve for k and c if we have two initial values. And we're given those values in that we know that every 7 years the population triples, and there are currently 100 birds. So at t equals 0, there's 100 birds. 7 years later, our population is tripled to 300. 7 years after that, our population triples again to 900, etc. So that's an exponential growth model because we're multiplying our population by the same thing per unit of time. So we'll solve for c and k. We know that p of 0 is equal to 100, but we also know that p of 0 is equal to c, so c equals 100. So we also know that p of 7 is equal to 300, and that's also equal to c times e to the 7k. Solving for k, I'm not going to go through all the algebra, we get k equals the natural log of 3 over 7. So our population model, p of t, equals 100 times e raised to the natural log of 3/7 times t. Or if you want to do the switcheroo, it's kind of nice to write it as 3 raised to the t over 7. Okay? Either or, your choice. By the way, we noticed that we also know that the k value is known, so that's that same k value here. So we know that dp dt is not just equal to some constant times p, we know it's exactly equal to the natural log of 3 over 7 times p. All right, and we can use this model to find the population at any given time. So at p equals 20, we're simply plugging in t equals 20 and getting, turns out, approximately 2,308 birds. If we try at t equals 40 years from now, we get 53,261 birds. And then 60 years from now, we get 1,229,167 birds. This population is growing quickly. Some may say it's growing exponentially. And that means, of course, that we have an exponential function that's modeling it. We're multiplying by 3 every 7 years, so that just means it grows really quick. The more we have, the faster we're growing. All right, so that's a review question, right? Nothing new about that. What we're asking now is to take a look at the slope field. So you can punch that into a calculator. At this scale, that Desmos slope field grapher is not great, so I'm going to use the TI Inspire. And you can see that I changed the scale so that I can see kind of the same scale as over here. And our differential equation is that natural log of 3 over 7 times our population. Our population is y1 in this case. Okay? So that is, I can kind of see my exponential curves here, right? I can give a solution, or sorry, an initial condition of 0 for t and 100 for p, and I'll see that gives us that nice exponential curve that we were given at the beginning, and that's the particular solution. But there are lots of other solutions, and we could consider other solutions, right, at different initial points, right? So, for example, we could try, I don't know, we could try 500. Why not? Let's see what happens if we add some initial conditions. I'll add 0, 500, and maybe I'll add 0, let's try a negative. Well, let's just stick to one at a time. Maybe I won't jump the gun here. So that blue one follows the same slope field. and goes through the point 0, 500. Okay, what happens if we look at a negative initial condition? Might not make sense, but with negative populations, but mathematically we have values down there. So let's see. And we can see that that red curve also follows the slope field. It's exponential with a negative c value instead of a positive c value. And we can keep on adding as many as we want to. Let's try 0, I don't know. Let's try -1 and see what that looks like. Well, that's fairly horizontal, so I'm not wild about that. Maybe I'll change that to 20. I just want to be able to see that curve. So you can see that it is horizontal for a while, and then it starts curving away. All right, so these are all just different particular solutions to that same differential equation. And you'll notice that dp dt is going to equal 0 for only one value of p. Okay? That one value of p is p equals 0. If the population is 0, then the population is going to stay 0. And that should make sense, A, because the slope is 0 when p equals 0. And, in real life, it makes sense. If you don't have any birds, then how are they going to make more birds? So there's exactly one value of p where we get that 0 value, and that is manifesting itself as that horizontal asymptote on every single one of those solution curves. So that's kind of answering this, how is it visible? And now I just want to think about what are some problems with this model. I think that this answer right here perhaps gives away what the problems with this model might be. It's unbounded, right? Growth is unbounded when we're looking at this exponential graph. And surely we're going to have some issues down the line when we get 1 million birds in a particular area. We're going to have too many birds, and there won't be enough resources to support them. And we're going to start seeing that rate of growth is going to decline. Maybe the population won't decline, but the rate at which the population is growing might start declining. And that's going to introduce a new concept called the carrying capacity. Okay, so there's going to be some sort of upper limit to how big our populations are going to be, and we can approach that upper limit, and it will be determined by a lot of different things. For example, how much space the population has to take up, how many resources there might be, like food and water and habitat, and also natural selection. Survival of the fittest sort of thing. So there will be some limiting factors so that our population will not grow forever to infinity, but it will have some upper level. We call that our carrying capacity. In the next video, we'll take a look at what the mathematical implications of introducing a carrying capacity are.